Alright, now in this video we'll be talking about inverse Laplace transforms. Okay, so we will look at some functions and their Laplace transforms, okay, from the table, and we'll take the inverse of their Laplace transforms. Alright, and I'm just going to show you those functions so that we'll just be applying them in solving some examples. Okay, so when we are given functions of t and we get their corresponding Laplace transforms, right? Okay, so we have that the function of t is for this column and it is equal to the Laplace inverse of the function of a's. So now when we have to take the Laplace transform, let's say the Laplace transform of a function of t, right? This right here will give us this function of a's. So that is how we denote it. So the Laplace transform of a function of t gives us a unique function, alright? By unique, I mean no two different functions of t have the same Laplace transforms. So to get back this original something, we just have to do this by taking Laplace inverse, alright, or you say inverse Laplace transform of both sides. So we denote it like this. So I'm just going to put that down. I'm now going to write everything here. This one, f of t. So this will give us the inverse Laplace transform of f of a's. Okay, so here we know that the Laplace inverse of the Laplace transform of function of t will just give us the function of t, alright, where this one and this one are inverses of each other, right? By composition of inverses, we get back the kind of argument, or yeah, okay, so that is just it. And here we have it to be the Laplace inverse of a function of a's. So we'll be working backwardly from the Laplace transform. Okay, so you just have to take note of this, that when we have a constant term, this k here is just a constant. For example, 5, the Laplace transform of 5 will give us 5 over a's. This outcome is always a function of a's for any function of t. So maybe you can decide to use p for your variable, for your a's. Okay, but it has the same definition. But mostly we use a's all the time as well. Now this denominator should be greater than 0. Here we have that this denominator should be greater than k, so it should not be less than, so that this right here will not be 0, right? No, that will not exist. Okay, so you observe all this, and when we have the function, the Laplace transform of t to power n, like this particular function, it gives us n factorial over t to the power of n plus 1. So if we have to compute the Laplace transform of, let's say, t to the second power, that is t squared, so we are just going to have 2 factorial, where the n is on the top, over t raised to the power of 2 plus 1, which is 3, like that, right? So that will give us 2 over t to power 3. So that is just pretty simple. You talk about the sine function and the cosine function, where the k is just a constant. Then for this last function here, well, I would let you know that this notation here means, now let me clean this part up and say a little thing about that. Okay, now if you are given, for example, e to power kt times a function of t, let's say cosine of t, alright? Let me use a instead of 1 as the coefficient. So I'm just changing this, I don't want them to be the same. So you know that when we have the Laplace transform of cosine kt, it's going to give us a's over a squared plus the k squared. So whatever constant you have here, you're going to square it. Now this notation here means that a function of a's, alright, you are going to replace a's with a's minus k, where k here is the constant that you're having in the exponent, right, in the power of e. Okay, so where k here is that, so this will give us is, now s will be replaced with s minus k. So we just put it down, s minus k, where the k comes from this exponent, right? Divided by a squared. So the s will be replaced with s minus k squared. Remember again that this k here comes from this one, right? Then the next thing we're going to consider is plus k squared. Now this other k is going to be from this constant, right? Maybe I just have to change this. Let me just change this for you guys to see, so it will not be okay. Let me put the k here. Let me change this one to a. All right, here, so we have here a squared, okay, and here will just be a. So that means we're going to be having s minus k over s minus k plus a squared. Alright, so that is just it. In place of s, you replace it with s minus k, where k is the constant here, and in place of s, you just do that, so that is something. Then in place of this a, just put the coefficient of t in the cosine function. Okay, that is just more about it. So we will be given complex functions, okay, to take their Laplace inverses, like something like this, but it will be more complex. Maybe we may require to decompose it or use different methods. Alright, okay, so let's get right into it.